Welcome to The Explainer. Today, we're diving straight into a critical dynamic that can literally make or break your entire power system analysis. We are putting on our senior planning engineer hats and tackling Phase 2, synchronous generator reactances. This is one of the most foundational yet dangerously misunderstood concepts in substation engineering and grid stability. Let's get right into it. So let me ask you a question right off the bat. Are you treating your generators as fixed impedances in your models? Well, if you are, I've got some bad news. Your fault studies are fundamentally flawed. Why? Because the instant a fault hits a generator, its current doesn't just behave like some simple resistor circuit. No way. The dynamics are entirely different. And honestly, getting this wrong has massive real-world consequences. Here's what's actually happening. When a fault hits the system, the current slams to this huge, violent peak, and then it decays chronologically across 3 distinct time-based stages over the next several seconds. The generator is literally fighting the fault in these 3 phases, and each one has a specific reactance value. We've got the subtransient reactance right at impact, the transient reactance kicking in around 0.05 seconds later, and finally, it settles into the synchronous reactance at steady state.
Let's break these down, starting with the absolute most severe. According to IEEE standards, this first stage is called the subtransient reactance, or X''D. At this exact moment, the machine presents the absolute lowest impedance it can possibly offer. And since the impedance is basically bottomed out, you get hit with the highest, most dangerous fault current. This happens the very instant the fault initiates and holds steady for just the first 0.05 seconds. It's a massive spike.
But, the generator doesn't stay in that state for long. Over the next fraction of a second, the internal magnetic fluxes in the machine actually start to shift. The effect of the damper windings decays, and the machine enters the transient stage. Now the impedance begins to rise to what we call the transient reactance, or X''D. During this window, which lasts for about a quarter of a second, that crazy initial fault current continuously decreases.
Finally, after several seconds, the magnetic field fully settles down. This leaves you with the synchronous reactance, or just XD. This is your steady-state reactancer in fault conditions. At this point, the generator is throwing up its highest impedance value, which drops the fault current down to its lowest point at steady state. So the big takeaway here? A generator's response is a moving target. It's a time-dependent decay curve, definitely not a fixed number.
Now you might be wondering, why are we getting so deep into the weeds of subtransient and transient decay right now? Well, understanding this chronological decay is more important today than it has ever been. The physical makeup of our global power grid is radically shifting, and it's placing grid stability at some pretty unprecedented risk.
Check this out. Recent grid stability research paints a really stark picture of our transforming energy mix. We're seeing solar PV making up 35% and wind power sitting at 30% of new renewable integrations. As these numbers climb, we are rapidly replacing the conventional, heavy, rotating synchronous generators that have historically stabilized our grid and gave us those predictable fault current curves we were just talking about.
This perfectly illustrates the divide. Traditional, synchronous generators inherently resist frequency changes because of their massive rotating physical mass. And hey, the geometry of that mass matters too. Cylindrical rotors on steam turbines have uniform reactance, while salient pole rotors on hydro units have protruding poles that totally change how they respond to disturbances. But whether cylindrical or salient, they provide mechanical inertia, reactive power, and high fault current. On the flip side, renewables like wind and solar are inverter-based resources. They connect through power electronics. They do not naturally provide any rotational inertia, and their fault current contribution is severely reduced.
In fact, if we look at the leading sources of instability in renewable-dominated grids, low system inertia takes the absolute top spot at 35%, followed by generation variability and voltage instability. Because we are losing that inherent physical stabilization, low inertia systems are incredibly sensitive to disturbances. This makes precise calculations of the remaining fault contributions from whatever synchronous machines you actually have left on your grid absolutely vital. There is literally no margin for error anymore.
Okay, so with the stakes this high, let's test this practically. Think back to those 3 stages of generator reactance we covered. If you were tasked with sizing a circuit breaker's interrupting capability, which of our 3 generator reactances should you use? The subtransient, the transient, or the steady-state synchronous?
You absolutely must use the subtransient reactance, X''D. Why? Because protective relays and circuit breakers are designed to operate incredibly fast. We are asking them to interrupt the fault in the very first few cycles. You have to size the breaker for the absolute worst-case scenario, which is the highest current it will ever physically see. If you use the steady-state synchronous value instead, you'd calculate a much lower fault current and disastrously undersize every breaker on your system. We're talking catastrophic explosions when a fault actually clears.
But wait, there is another hidden danger lurking in that initial subtransient window. Even if you use the correct subtransient reactance, the actual fault current isn't a perfect symmetrical wave. It's asymmetrical. It features both an alternating AC component and a unidirectional DC offset. If you ignore this DC offset, you are still underestimating the true thermal and mechanical stress on your equipment.
Let's define this clearly based on the IEEE standard. DC offset is simply the difference between the symmetrical alternating current wave and the actual current wave during a transient condition. This unidirectional component can be either positive or negative polarity, and it won't change polarity. Instead, it just decays at a predetermined rate over time. What this means in practice is that the initial hit to your substation, especially your grounding grid, is far, far worse than a simple symmetrical AC wave suggests. To compensate for this severe asymmetrical hit, safety-oriented grounding calculations require you to use a decrement factor. This factor, DF, determines the true RMS equivalent of that asymmetrical wave over the entire duration of the fault. Basically, it accounts for both the severity of the initial DC offset and how quickly it attenuates, or decays, while the fault is actually active.
Building this into our overall grid calculations, the initial symmetrical current is driven directly by that subtransient reactance we discussed earlier. By applying the fault current division factor and then combining it with our decrement factor, we arrive at our absolute worst-case maximum grid current. This right here is the true bedrock of safe substation design.
Now you might be asking, okay, but what determines how fast that dangerous DC offset actually decays? Well, it's entirely dependent on your system's X/R ratio. That's the ratio of system inductive reactance to resistance at the fault location. A large X/R ratio means the system is highly inductive. That corresponds to a large time constant, which results in a dangerously slow rate of decay for the DC offset. So the offset just ungen massive amounts of thermal energy straight into your grid. And this data directly impacts the physical reality of the substation. According to IEEE standards, if you have a high X/R ratio, say around 20, the allowable current for a given copper grounding cable size drastically reduces the longer the fault persists, from 6 cycles all the way up to 180 cycles. If you've got a high X/R ratio and a slow clearing time, you are forced to use significantly larger, way more expensive copper cables, like 4/0 or even 350 kcmel, just to keep the grounding grid from literally melting under the asymmetrical fault energy.
So let's tie all of this together with one final thought. If you fail to use the subtransient reactance, or if you ignore the decrement factor and DC offset, you are going to undersize your breakers and your grounding grids. What happens when those undersized components fail catastrophically on a modern power grid that's already operating on the razor's edge of instability due to low renewable inertia? Getting these dynamic stages wrong doesn't just mean a failed calculation in some textbook, it means triggering cascading blackouts in the real world. Thanks for joining me on this explainer. You came in thinking of a generator as one fixed impedance, and now you know how they actually fight faults. But remember, generators are only half the substation. Next time, we're opening up the steel tank to uncover the hidden dynamics of transformer equivalent circuits. See you then.